Welcome back to the Master Course Explainer. Okay, let's dive right in. Today, we're tackling a massive and honestly, absolutely crucial topic, bridging the gap between the idealized perfect world of 3D CAD designs and the messy, harsh physical reality of the shop floor. We are getting deep into CMM programming, measurement strategy, and GD&T inspection. Now, if you've been following along with the course, you already know how to apply geometric tolerances on a drawing, but Today is all about how we actually prove that those physical parts meet those strict theoretical requirements. I want you to picture something for a second. Imagine a super complex aerospace bracket, or maybe an intricate automotive engine block. We're talking hundreds of highly specific features, complex curves, super tight positional tolerances, the whole shebang. So here's the big question. How on earth do we inspect geometry that is nearly impossible to verify manually? Traditional hand tools like calipers and micrometers are great, we love them, but they simply aren't enough when you're dealing with strict three-dimensional geometric constraints. We need a system that can literally translate the physical world back into the mathematical language of our designs. To get there, here's our structural roadmap for today's explainer. First, CMMs and GD&T basics. Second, datums and measurement planning. Third, inspecting controls and reports. Fourth, CMMs versus functional gauging. And we'll wrap up with number 5, common inspection mistakes. All right, kicking things off with section 1, CMMs and GD&T basics. Let's start with the big one, the ultimate tool for complex verification, the coordinate measuring machine, or CMM. Now, the bedrock of modern CMM workflows is model-based GD&T. Historically, an operator would have to manually read a 2D print and then try to program a machine to inspect it. It was tedious. But in modern workflows, the 3D CAD model is the absolute authority. Model-based inspection essentially means we're bouncing quality-controlled data directly against that 3D CAD model in real time. By doing this, we automate the inspection planning phase, and crucially, we preserve the true design integrity. There's zero manual translation error from the print to the program because the intelligent GD&T data just flows straight into the metrology software. It's a total game changer. The workflow here is actually beautifully structured. Step 1, you just open your 3D CAD file right in your metrology software, and boom, it brings all that intelligent GD&T right along with it. Step 2, the software actually helps you create an automated inspection plan. So say you have some really complex composite position callouts, the software is going to group them and apply the necessary alignments for you. Step 3, you run the physical inspection using your CMM, letting it follow the programmed probe path. And finally, Step 4, the software instantly displays the measured deviations with a crystal clear pass or fail result. It honestly takes the guesswork completely out of the equation. Moving right along to Section 2, datums and measurement planning. So before a CMM can measure even a single feature for deviation, it has to know exactly where that physical part is located in 3D space. We lock that part down using a datum reference frame. If you look at how this breaks down according to the ASME Y14.5 standard, every single time we establish a datum, we're constraining specific degrees of freedom. For instance, if your primary datum is a planar surface, a plane, resting the part on that plane constrains 1 translation and 2 rotations. Basically, it can't move up and down, and it can't pitch or roll. If your datum is a cylindrical axis, well, that constrains 2 translations and 2 rotations. And a spherical point, that constrains 3 translations but 0 rotations. A CMM actually creates its coordinate system by physically probing these primary, secondary, and tertiary datum features in strict succession, mathematically locking the part in space before it even thinks about measuring anything else. But here's where we had a bit of a reality check. As we move from theoretical datums to actual measurement planning, things get messy. Do we always measure in a perfect, climate-controlled 20 degrees Celsius environment? Absolutely not. Do we take an infinite number of points on a part's surface? Impossible. Do we use measuring equipment that has exactly 0 error? Never gonna happen. Every single measurement you take is an estimation. That's just the truth of it. The reality of measurement planning is that we are constantly having to balance the cost of the measurement against the required accuracy. Sure, you can always take more points or run the probe slower, but in manufacturing, time is quite literally money. We have to manage our uncertainty intelligently. Okay, Section 3, inspecting controls and reports. Once we're perfectly aligned and have our strategy set, what exactly are we asking the CMM software to evaluate? Well, it has to mathematically interpret specific GD&T symbols. Let's quickly review 4 common ones. Circularity, that single circle symbol, defines a 2D tolerance zone. The The CMM just looks at a single cross-section and verifies all the points fall between two concentric circles. Cylindricity, on the other hand, is a full 3D measurement. The CMM actually has to scan along the entire length of the feature. True position, the famous crosshair, relies on your datums to define exactly how much a feature's location can vary from its perfect intended spot. And total runout, those two arrows, measures 3D surface wobble. It does this by taking multiple points across an entire surface while simulating a full 360-degree rotation. Knowing whether the symbol on your print requires a quick 2D slice or a comprehensive 3D surface scan is absolutely vital for programming your CMM correctly. And the really crucial part of all this is how we visualize that data once we have it. When you look at a highly detailed 3D topographical plot mapping these high-resolution surface deviations, it's pretty incredible. A modern CMM or optical scanner doesn't just spit out a single boring number anymore. It creates this rich, high-resolution map of the deviations. The red peaks instantly show you where the physical material is higher than the nominal CAD model, and the blue valleys show you where it's lower. This gives a quality engineer the ability to immediately see the actual surface texture and form errors, sometimes down to the nanometer scale, and compare it right against that perfect geometry we envisioned back in the design phase. We see this exact same advanced reporting applied to larger features too, using color maps for super rapid pass-fail interpretation. Instead of forcing you to stare at a giant spreadsheet of raw X, Y, and Z coordinate data, the metrology software just visually highlights the problem areas for you. Green means you're good, the surface is well within tolerance. But as it shifts into yellow and red, you know the surface is out of tolerance on the high side. Dark blue, that's the low side. For a manufacturing engineer, this kind of visual feedback is absolute gold. It doesn't just tell you that a part failed. It shows you exactly how it failed, which points you right back to the root cause in your machining process. Moving into Section 4, CMMs versus functional gauging. So, as amazing as CMMs are, they definitely aren't the only tool we've got in the shop. How do you actually choose your verification method? Well, it usually comes down to this core comparison. CMM inspection is fantastic because it handles incredibly complex 3D geometry and gives you exact quantitative deviation data. But it is relatively slow and it definitely carries a higher cost per part. On the flip side, we have functional go, no-go gauging. I always like to think of this as a highly engineered version of a toddler's shape sorter toy. It uses physical pins and blocks to physically simulate the datums and the worst-case boundary conditions of the part. They are extremely fast, making them absolutely ideal for high-volume mass production. The catch? They only give you a binary result. The part fits or it doesn't, pass or fail. You don't get any of that rich data telling you why it failed. But make no mistake, both of these methods have a crucial place in any modern manufacturing environment. Finally, Section 5, Common Inspection Mistakes. Even with million-dollar CMMs and perfectly machined functional gauges, human error is, well, it's always lurking, right? Here are the most frequent pitfalls you absolutely must avoid. First, overcomplicating your designs with super tight tolerances that aren't even functionally necessary. All that does is drive up CMM programming time and manufacturing costs. Second, misinterpreting or picking non-functional datum references. Listen to me on this one. Never pick an imaginary point in space as a datum, and don't pick a surface just because it's convenient to measure if it doesn't represent how the part actually functions in real life. Third, confusing your material condition modifiers, maximum material condition versus least material condition, stuff like that. Fourth, completely ignoring how tolerances stack up in an assembly. And lastly, selecting unstable datums that actually cause propagated measurement error. Because if your physical alignment is flawed from the start, every single measurement your CMM takes after that is going to be wrong, and you're going to end up making perfectly good parts look like scrap. Let me share a famous real-world example with you. It's known in the industry as the so what case study. Imagine a drawing with a parallel constraint pointing clearly to datum A. But out on the floor, an inspector places the part on surface B, the bottom edge, and measures from there instead. When someone points out they're inspecting the wrong datum surface, the inspector shrugs and says, "So what? Surface B is parallel to datum A, so what's the difference?" The difference, my friends, is literally everything. If datum A and surface B aren't perfectly parallel, and spoiler alert, in the real world they never are, you are instantly introducing an unknown angular error into your measurement. You must strictly follow the datum reference frame exactly as it is called out on the drawing. Assuming things are close enough is a critical point of failure every single time. And get this, even if you get the datums perfectly right, you still have to watch out for something truly wild called methods divergence. This happens when your CMM software offers you different mathematical algorithms to fit a shape to your data points. Let's say you're measuring a circle. Your software could use a least squares fit, or it could use a minimum zone fit. Both are completely mathematically valid, but if your physical part has an odd, sort of lobed shape from the machining process, these two methods can yield completely different center points and completely different diameter sizes. You could literally have a part pass inspection using one math algorithm and fail using another. As a programmer or an engineer, you have to deeply understand exactly what mathematical method your software is running behind the scenes. All of this brings us to a final kind of provocative thought I want to leave you with today. GD&T is fundamentally designed to unite the ideal design world with the physical, messy realities of manufacturing. But if our inspection methods or our datum setups or even our software algorithms are introducing propagated error, are we really verifying the part's quality, or are we merely measuring our own mistakes? The tools we have access to today are undeniably powerful, but they require a deeply educated user to ensure that what we report on the screen actually reflects the true physical reality of the part on the table. And that wraps up our explainer on CMM measurement strategies. You've now seen exactly how we connect the theoretical CAD model to the physical inspection process. Next up in the master course, we're going to be looking at advanced drawing interpretation and GD&T workflow. So keep practicing, keep analyzing those prints, and I will see you in the next lesson.